Gonna have to face it, you're addicted to love. I see the signs, but you can't read, you're running out.
Hello and welcome to the video on the Fundamental Theorem of Calculus, Part 2. Okay, so here's a refresher. Let's just go take a quick look back at the Fundamental Theorem of Calculus, Part 1. So that was basically using, we used the antiderivative, so our capital F of x, right? So we use the antiderivative to compute the integral, an integral. So that looked like the following. So we had integral from a to b of some f, lowercase f of x dx, and that was equal to the antiderivative, so capital F of x, and then evaluated from a to b, which was the same as saying we're evaluating at the top limit and then subtracting when we evaluate it at the bottom limit. Okay, so that's what we were doing in the part 1 of the Fundamental Theorem of Calculus, and now in part 2 what we're going to do is kind of the opposite. We're going to use the integral, so we're going to be using the integral to compute to construct an antiderivative. Antiderivatives. Okay? Alright, and what this looks like is basically saying that our antiderivative, this thing, okay, so this is going to be our I'll just call it antiderivative. Okay, that's going to be equal to the integral, so we're going to use this integral, we're going to start at some constant, a, and go up to x. And then we have some function in here, f of t dt. Okay, so this is going to be equal to the signed area. So again, signed just means positive or negative. So signed area from a, x equals a, to some x value. Okay, so this is, pictorially, this is what it looks like. So we have, let's say, here's x, here's y, and we have some function going along, right? So something like that. Okay, so let's say we start integrating at a. Here's a. And then this means, what this notation means is that up to some x, if we go up to some x, so let's say x is here first of all, and then that would give us the area under the curve up to there. But now let's say we choose a different x, okay? So now we're going up to here, all right? And then we'll just keep going, computing that area, all right? So whatever x we choose, this is the function that gives us the signed area, how much we have from a, starting at a, up to whatever x value that we are given, okay? Alright, so that's what it shows us. So here's an example of the second part of the FTC. So let's say that our a of x is equal to the integral from 3 to x of t squared dt. Okay, so what will we do with this? Basically, we would just kind of integrate like normal, right? So we're just going to integrate, so we have t cubed 1 over 3, according to the power rule, right? And then we're evaluating it from 3 up to x. And now our upper limit just happens to be this variable instead. So our a of x is going to equal, so let's plug those in. So we get 1 over 3 times x to the third. So that's when we plug in the upper bound, and then we can get a 1 over 3 times 3 to the third. So that's when we plug in the lower bound there, or the lower limit. So a of x is going to equal 1 over 3 x to the third, and then this is going to be minus a 3 squared, so that would be minus 9. Okay? So this is the formula. This is our antiderivative, and that gives us the signed area from 3 up to some value x, right? This is basically another kind of function. Okay, so now let's go one step further, and we'll say that, so given that a of x is equal to the integral from a up to some value x of f of t dt, and here we just use t's instead of x's so that we know that these variables here, whatever we're using is different from our, it's a separate thing from our bound here, that x, okay? So anyways, we're going to go one step further to complete the circle, and we're going to say, let's say we differentiate with respect to x on both sides. So if we ddx both sides, what we get is ddx of a of x, and then ddx of this integral from x to a of f of t dt. So on the left side, what happens is we get a prime in there, like that apostrophe thing, right? And then so the first derivative of our antiderivative now is going to be basically just our function with whatever our upper limit was plugged in. So that would be f of x. Okay? So this shows that that a of x truly is the antiderivative of our function. Okay? Alright, so that's basically it. And now on the next slide, I'll state the Fundamental Theorem of Calculus Part 2 formally. So basically what it says is FTC2 says that assuming, because we always like to assume things when we're writing a theorem, right? So assuming our f of x is continuous, So continuous on, and here we have an open interval I, we're going to say, and we're going to let our constant value a be in I somewhere. Then the area function, so that means area under the curve, right? Area under the curve function, our capital A of x is equal to the integral from x to a of f of t dt is an antiderivative. Of f of x, derivative of our f of x on that interval I, And additionally, that means that a prime of x, because it's an antiderivative, that means that it is equal to our f of x. So a prime of x is also equal to, it basically means that this is the font, like I did on the last slide, right? That shows why it's equal to our original function f of x, okay? Which these kind of cancel, but we're going to plug that guy in there, the top limit, so f of x, all right? And then the last thing to note, this is also part of the fundamental theorem of calculus part 2. If we were to plug in an a into our original area function, we would get the integral from a to a of f of t dt, which, as we know, when our limits of integration are the same, that means we don't really have any kind of area existent under there. So that means we're going to get a 0. Okay? So this is all of the second part of the fundamental theorem of calculus in its entirety. And now let's tackle some problems. So the first problem that we have is going to express the antiderivative. I'll just abbreviate, capital F of x of f of x satisfying the following. So satisfying the following condition that capital F of 5 is equal to 0 for our function f of x, which is equal to square root of x to the third plus 1. Okay, so how are we going to set this up? So we have that f of x, capital F of x, we want that to be a integral from a to x of f of t dt. Okay, so the first thing that we're going to do is simply, it's a really simple step. We just want f of t, lowercase f of t, so we're just going to plug a t in for the x spot. So f of t is going to equal the square root of t cubed plus 1. Okay, so that part's done. We got that. And now we don't know what our a is, right? X is just going to be x in the end, but we don't know what a is. So let's use another piece of information that gives us a little hint. So we do know that f of 5 is equal to 0. And remember before from the very last thing that I wrote for the fundamental theorem of calculus part 2, we said that f of a is equal to 0 because when you plug in a to a, if you plug in that a there, then we're just going to get like a non-existent area, right, which is 0. So that means that our a down here, that one must be a 5. Okay, so in this case, f of 5 is equal to 5 up to 5. So this one should be our constant. That's what it tells us, is that that's going to be our lower limit there. Because when we plug in 5, then that makes our integral 0. Okay, so anyways, so our a is going to be equal to 5, and now we can plug everything in. So we have a equals 5, and we have our f of t, and that's pretty much all we need. So our answer is going to be f of x, capital F of x, is equal to the integral from 5 up to x, and then our f of t is the square root of t cubed plus 1, and now we have a dt there. Okay, so that's basically it. All right, and you can always go back and check, given the initial condition there, plug in a 5, and then you're going to get that the top limit there is 5, and then we get that the area is a 0. Okay, so let's do one more example. What we're going to do is find the derivative, now not the antiderivative, but the normal derivative of, let's say we have the function a of x is equal to the integral from 2 up to x of 1 plus t cubed, and then our dt. Okay, and we're going to calculate a prime of 2. Okay, so first of all, we have to find a prime. So we want to find the derivative of that. So that's going to be d dx of our a of x is equal to a prime of x. Okay, and that's going to be d dx of the function from the integral from 2 to x of 1 plus t cubed dt. Okay, so this one here, according to the FTC2, these are kind of going to cancel out, but we want to plug in an x wherever we see a t. So a prime of x is going to be a 1 plus, not t anymore, but an x cubed. And that's pretty much it. So we found our derivative of a, of the area function, and now when we plug in a 2, we basically just get 1 plus 2 cubed, and then this is all under square root. So that's going to be a 1 plus 8 under the square root, which is square root of 9, which is ultimately a 3. Okay? Alright, so one last note on this fundamental theorem of calculus, part 2. Let's say, what if we're dealing with composite functions? So, you know how whenever we see a composite function, that gets a little bit trickier. So before we've adapted for composite functions using chain rule and stuff like that, right? So that's actually what we're going to be doing here. So let's say our g of x instead. So g of x is the integral from -2 up to x squared instead of just an x of sine t dt. So here we have a little bit of a dilemma, right? Because this isn't just a single x anymore. So not a single x, not just like an x to the 1 power, right? So what are we going to do with it? So what this is we actually consider this x squared like an inside function. Okay, so this is our inside function of the composite function. So inside function, and usually it's considered a u of x. So u of x, our inside function, is x squared. So what that means is when we differentiate both sides, so if we ddx the left side and we ddx the right side, ddx of -2 to x squared and then sine t dt, this is what goes on. This is how we're going to use the chain rule. So our g prime of x is now going to equal, so what we have to do is integrate with respect to the outer function first. So that would just be like if we were to replace this guy with a u. Okay, so that would, because this is our inner function, right? So we don't want to consider like what's going on inside that upper limit yet. We're just going to consider it, it's just something there right now. It's holding a place. Okay, so here, in this case, what I mean by that is we could actually rewrite it as like d du of -2 up to u, because we're not considering what's actually going on in this upper limit, and then sine t dt, and according to the chain rule, then we'll have this multiplied times whatever the derivative of the inside function with respect to x, the one that we want. Okay, so let's continue this on the next slide. So we have g prime of x is going to be equal to, so now we have d du of the integral of -2 up to u of sine t, okay, and then dt, and then on the outside we had this du dx, because this is from the chain rule. Okay, so if we integrate with respect to the inside, so again, here's a refresher, u is equal to x squared. Alright, so g prime of x is actually going to equal, so if we take this, then the fundamental theorem of calculus part 2 says that we just plug in a u here. So that's just going to be sine of u, whatever that is. Okay, we'll replace it with x squared later on. And then we have du dx. So that'll be the derivative with respect to x of our u, which is x squared. Okay, so now what we're going to do is have this sine of u, and we can replace that with an x squared, right? And because that's equal to u. And then the derivative of x squared with respect to x is simply a 2x. Alright, so basically we just have g prime of x is equal to a 2x times sine of x squared. Okay, so now that we've done that problem, that example there, let's come up with, well, we'll state the general chain rule for integrals. Chain rule for integrals, okay? So this is going to look like the following. So let's say if our g of x, like we just saw, right, is actually an area function with a u of x built inside. So u of x was our inside function, that was the upper limit, right? Where a of x is equal to the integral from a to x of some f of t dt. Then we have that, so then, comma then, we have that g prime of x is equal to a prime of u of x times u prime of x. So that just comes from the chain rule, right? If we have this given composite function, then this is what we get. So according to our formula, though, the area function, then that also means that g prime of x, that looks like a 6, sorry, g prime of x is equal to not a prime anymore, but now we have If a prime, then we have that f of x, but instead of just an x, we have a u of x, okay? F of u of x times the derivative of u with respect to x, okay? So it gets a little bit complicated here, but basically what this means is that whenever you're, so I'll draw it on the next slide. So let's say we have our g of x is equal to, let's do the other problem, right? So if I just write this again, so sine t and then our dt, so basically what you're going to do is just, according to the second part of the fundamental theorem of calculus, we're just going to, when you take the derivative, we just plug this guy in for the t spot. So that's what we're going to have. We're going to plug that in there. And then the only other thing is to add on or multiply the derivative of the inside. So that'd just be our 2x. That's the way I think about it. It's a lot simpler. But that's basically what's going on, an overview of that. Okay? Alright, so that's it. That wraps up our concepts video for the Fundamental Theorem of Calculus Part 2. I hope that helps, and good luck on your homework.